if you look at the one, should be the first one in your handout, that's about an environmental engineering team determining the quality of air in downtown Minneapolis. I didn't number these, I forgot to number them, so if you just, they're front and back in the order you got them, they should work out just fine. So, just trying to have a real application problem to this stuff. Somebody has to use this physics stuff to actually make these things work. So, air quality, obviously somebody measures it somewhere, and they have some toys that are able to do things like pick up pollen, which this problem's about, or this one's not about pollen, another one's going to do. But this spectrum analyzer is one way to determine what's in a gas. And so if you read down through the middle of the problem, you got to calculate the expected angular velocity for these O2 molecules in the air. And you're given some information. Mass speed of a typical molecule is about 500 meters a second. And atomic sizes, it should be about 10 to the minus 8 centimeters, or 10 to the minus 10 meters. You also know that you can look up the mass of an oxygen atom, which is pretty darn small. And the boss, finally, last sentence tells you to assume that the rotational kinetic energy is going to be equal to 2/3 of the translational kinetic energy. So, given this fact, okay, that the rotational energy is going to be about 2/3 of its kinetic, we could move straight to the equations based on that assumption. So I know that rotational kinetic energy is always 1/2 I omega squared, or the rotational inertia, moment of inertia, times the angular velocity squared. And I'm told that that's 2/3 of k, which is 1/2 mv squared. So our translation of the rotational kinetic energy of the molecule rotating about an axis through the center line is about 2/3 of its translational kinetic energy. So 1/2 I omega squared, the rotational kinetic energy, is 2/3 of that 1/2 mv squared, or the regular straight line kinetic energy. All right, so now it's relatively simple. We want to know what this rotational speed is. So it's just dropping things out. So the halves are going to fall out for us. And I'll have omega squared is going to be equal to, keep this 2/3, and I'll have an mv squared on top still. This I is just going to be, since it's a particle, a sphere is just an mr squared, a point particle. If you remember when we first developed this idea, it just ended up being mr squared. And so that I results in just having an mr squared. Well, once again, the masses are going to drop out for us, and omega squared is just 2/3 v squared over r squared, which means if you take the square root of all that stuff, then omega would just be v over r, which that's a familiar formula. It should be. That's our v equals omega r is our go from linear to angular speed. So we already have that factor coming out, but that 2/3 is stuck under the radical. So really, this sort of meets our expectation, or at least it should. If I want to know the angular speed of something and there's some sort of relation to the linear speed, then it's just going to be a factor of v equals omega r, or in this case omega is v over r. And if the rotational energy was 2/3 of the kinetic energy, it's unsurprising that the rotational speed is going to be some factor of what it otherwise would be. All right, so we get a reasonable conclusion here, and so now we know how to go about figuring out the angular speed, which is going to be totally related to its linear speed of the thing. So that's a pretty simple one. There was a lot of information in the problem that didn't matter. We didn't need to put the mass in because the mass didn't matter. All right? And so these speeds, if you convert this speed, it's basically in the ballpark of what a gas, average speed of a gas molecule would be. And so that's that one. Just a simple application of the equations that we know. Now moving on, the next problem is you're working on your latest novel about settlers crossing the Great Plains in a wagon train. All right, so you and your co-author are trying to figure out how to work out the rotational inertia of a wooden wagon wheel. All right, so we're told in this problem that the mass of this wheel is 70 kilograms. We're told that its diameter is 120 centimeters, so that means its radius of the wheel is going to be 0.6 meters. So just translating like that. And the co-author claims that you can approximate using I equals mr squared, okay? And we'll find out whether or not that's true. But you think it's going to be less because the spokes pulling mass in towards the middle makes the rotational inertia smaller. All right, so this is that skater idea. You extend your arms, you slow down because there's more inertia out towards the edge. If you pull them in, more mass is more concentrated in the center, it speeds up. Less rotational inertia in that regard. So we're going to find I experimentally. Okay, and so to do that, as it says in the problem, you could put your wagon wheel, we don't know how many spokes it has, so we'll just make up something here. And we could, wrap some stuff around it or even on the edge if we wanted and drop some mass. And see, what's the time of flight for the bag that drops when it hits the ground, okay? And that sort of thing. So the idea, the mass of the sand, you can call that MS, is 20 kilograms. And the height that it drops through, okay? Height's 3.77 meters. Change in time for that drop, 1.6 seconds. So all that data goes through one complete turn. So we need to first, let's find the speed of bag at impact, or just before impact. So what we can do, I know that if I use the first zeroth law in its general form, it says that delta S equals V bar delta T. The difference being is that I have a delta Y here in my situation. The average speed I could write as the final Y speed plus the initial Y speed over 2 times this delta T. All right. Well, my initial Y speed is 0. So that drops out. And I have, if I solve this equation for Vy, I'll just get, multiply both sides by 2. That wasn't very good too. There we divide both sides by delta t, and I get my Vy is just really just 2h over t, and I get 4.71 meters per second out of that. And using that V equals omega r business, that means that my angular speed is going to end up being 3.93 rads per second. I trust you can plug and chug those numbers if you need to. So right off the bat, I have my linear speed of the bag, and since that piece of rope is connected to the speed of the wheel, that's going to be the max speed of the wheel before impact. You get the angular speed from that conversion there, because the rope is moving at the same speed that the bag is. Every dot on the rope is. All right, so I can just use one of those dots, angular speed, to get my answer. So I have the speed of bag of at impact part of this puzzle. Now we need to do the energy balance. By the way, I'm doing these problems all in the same basic fashion, and so you need to follow this general pattern of kind of section heading your work so that you know what to do. And all we did in this first part was basically just use good old kinematics. Old news about speed. It was an easy kill to get the speeds. So always go for the throat on whatever's the easiest to compute, and then save the main topic area for the last thing you do. Otherwise you write it out and you have all these big equations, and then you have to go back and find something else. So energy. So let's think about this issue. Initially the wheel ain't moving. You just have a bag of sand attached to a rope attached to the axle. And if you let that bag go, the bag will fall under gravity. So initially, the only energy in town is gravitational potential energy. And that gravitational potential energy is going to go into the kinetic energy of the wheel and the kinetic energy of the bag. Because that's what the result. Giving away all of that gravitational potential from releasing it from rest at some height to the ground results in two kinds of motion. The wheel going roundy-roundy and the bag going downy-downy, right? Two kinetic energies splitting up whatever that gravitational potential is. This is why energy is a nice way to work these problems out as opposed to a force analysis. Well, the gravitational potential energy is just mgh. We've done this a few times. Kinetic energy of a wheel, a rotating thing, would be 1/2 I, whatever the rotational inertia is, which we don't know yet. And then the kinetic energy of the bag would just be 1/2 mass of the sand and this Vy squared. All right. Oh, I have to correct something here. That speed, the angular speed, not 3.93, it's 7.85. Sorry about that. And this mass over here on the gravitational potential side is also the mass of the sand. So if I solve everything for I, all right, so obviously to get I by itself, here's another thing we could do and will do here, is if I just multiply through by 2, everything gets multiplied by 2. If that's the case, then these 1/2s go away, and I just have a factor of 2 on the other side there. And so I'm going to have this mgh on the left minus the mv squared on the right. And then I'm going to divide away that omega squared. So this equation, just solving the energy balance for the rotational inertia. This will be an experimental way to find the rotational inertia of this wagon wheel, which we don't know anything about except its total mass. Didn't tell us how many spokes, didn't tell us any of that. All right? If we knew how many spokes and what the mass of the spokes were, we wouldn't need to do any of this. We could just have the rotational inertia of the outer wheel and add up the rotational inertias of the sticks. Those are two different formulas, and we would know, we could just compute it. Okay? So this experimental data lets us do it through a different means. And so if you plug and chug, put mass of 20 kilograms in for the mass factor, the gravity is 9.8, the height is 3.77, and this linear speed of 4.71 squared over the angular speed of it not squared. You'll go through all that rigmarole, and you should get 16.8 kilogram meters squared. That's a weird unit for rotational inertia, but it is related to an area in that it's an extended body of all things. So that's the experimental result for the rotational inertia using energy as our guide to figure that out. So in the problem, if you look back at it, is the rotational inertia of the wheel equal to mr squared? Because that was the hypothesis of your co-author in this story that we made up. And so if that's the case, what's mr squared? Well, mr squared, the mass of the wheel, okay, so this would be our capital M, if you will, 70 kilograms, and the radius of the wheel would be our 0.6 meters squared, and this works out to be 25 kilogram meter squared. So it looks like it's not a good approximation. All right, that seems to be off by a lot. You know, so I would say no, co-author, not close enough. All right, but what it does confirm is that if all of the mass was concentrated at the radius, that's what that mr squared is telling you, is that the mass is out there at the edge, this radius away from the center. And if all the mass were concentrated in the wheel, then the rotational inertia would be 25. Our experimental apparatus, because apparently the spokes are heavy, as the problem states, tells me I already know, in fact, I should know in advance that that can't be true. Okay, so this is the tough thing. You get a lot of equations thrown at you in the course. Why would I need to go through the experimental thing? Well, to prove to your co-author that they're wrong, I guess. But it validates, I guess, the theory that's laden in all these equations. And so you can see, if you've ever seen a figure skater, you know, if I am spinning with my arms out and then I pull them in, I will speed up. And the reason I'll speed up is because the mass is concentrated closer to the middle. And that means if I speed up, it's because there's less inertia now. Newton's first law. All right? If more mass means more resistance to motion, less mass means less resistance to motion, and mass isn't just a density idea, how much stuff is packed into a volume, it's how it's distributed. Okay? So The only way that this would work out to be the same is if the wheel had 3 spokes. Because when you look at the rotational inertia of a rod, okay, a stick, so this is a little free sidebar here, is 1/3 ml squared, length of the rod. So if I had 3 spokes, then it would be mr squared, but that would just be dumb luck. But we weren't told how many spokes. Usually you have more than 3 spokes. Okay? And if you look at like a lot of like your bicycle tires, they have a lot of spokes, but the mass of those spokes compared to the mass of the wheel is small. Okay? So that's that. So our co-author was not fully informed. We can reject that idea. All right. One is summer job at the Winter Olympics. Designing ceremonies. So basically you're going to have these big Olympic hoops, you know, because the Olympic symbol has all those 5, 6 hoops, whatever it is. And so skaters are going to run out and grab one of these hoops that's stuck to a pole and go roundy, roundy 5 times. That's the goal of this problem. And our assignment in the last 2 sentences there, 3 sentences, determine the minimum speed that the skater has to have before grabbing the ring in terms of the radius of that ring, the mass of the ring, the mass of the skater, and the frictional force between the skates and the ice. Choreographer wants the skater to go around the pole 5 times. So really, if we're going to have the skater skate out, grab that ring, and just kind of free glide around it 5 times, that pole that it's attached to, how fast do they have to be going so that they don't have to give themselves an extra kick to keep going around? All right? So we have a length to chart out for the friction force here. All right, so let's get at it. First thing we got to do is the momentum has to be conserved. We talked about this briefly in another thing, but when you have a collision, the first thing you need to do is conserve the momentum. And from that momentum conservation, inevitably you get the speed term that you need. So what's the collision? The skater with the ring. And so whatever speed via momentum that the skater and ring system obtains, then that energy transfer between the speed that's going into the system and the energy that's being quote unquote drained out of it by the work done by friction. All right, so but we got to conserve momentum first. So I have angular momentum. So remember the strange fact of L for angular momentum. So the initial angular momentum needs to equal the final angular momentum. So that means the initial rotational inertia, moment of inertia, and initial angular speed have to equal the final moment of inertia times the final angular speed. This is the same as mass times speed equals mass times speed, except now it's inertia times angular speed equals inertia times angular speed, initial and final versions. All right? So we go to town. Rotational inertia is going to be the mass of the skater. We'll use a capital M for that. So mr squared. So just so you know, initial rotational inertia, mr squared. We're treating the skater as a point particle at that connection for the thing here. And then omega squared, or omega, remember, V equals omega R, so that means that omega would be V over R. So we could just write, instead of omega, we could write initial speed, linear speed, R, because that's what the skater's going to have at the collision. the skater's going to be skating in a straight line at some linear speed. So I've got to get this into the linear speed, because that's the question. How fast does the skater need to be going? All right, and so we can go test that later so the skater knows what it feels like to go the right speed. All right, because as long as they have that speed or bigger, this will work out just fine. So left-hand side of the equation settled. Now, the right-hand side here, what's going to be true about the angular momentum? Well, going in, it's just the skater's momentum. But as soon as the skater and the ring connect, now I have the skater's mass and the ring's mass. So this is going to be, the rotational inertia would have to be the total mass of the system, r squared, okay? And that would be v over r, because it's the final speed, etc. I need to write my squared term a little better here. Slightly better. So now we've conserved the momentum. What we can do is we can go through here and say, well, one of these r's wipes that one out. Same on the other side. And I have a factor of r that's common to both sides, so I can wipe them out as well. And that leads me to mv naught just equals m plus m times v, which is sort of unsurprising because it sort of just shook out to be what we would expect if it was particles that stuck together. Because if a big m mass at some speed runs into a little m mass and they stick together, wouldn't it be that final momentum would be the sum of their masses times that new speed? So it boiled down to conservation of angular momentum looks just like conservation of linear momentum in this case. All right, so at least we get something that makes a little bit sense. And what this tells me is if I want to know final speed, I can write it as the fraction, the mass fraction, times the initial speed. So basically, the final speed after the collision is going to be a little less than the initial speed of the skater. That makes sense because the skater just added inertia. The skater just added resistance to motion to the system. So that it would have to slow down. This guarantees a smaller speed because the biggest speed in town was that initial speed. All right? So we have all of that. Now we want to conserve energy. Give myself some space on the side here. You don't probably need to do that on your papers. So what do we have? Initially, we have the kinetic energy of the system, which is all wrapped up in the skater. All right. So that's going to be a half mass of skater, initial speed squared. Then all of that goes into the kinetic energy or rotation of that ring, plus the work done by friction. Okay? Well, let's deal with the kinetic energy of the ring. So again, this is going to be 1/2 I omega squared, and this is going to be friction times the length, the path that friction does work on. So I want you to note something because we're getting thick into the weeds of equations here. None of this is new information. Everything we're doing in this unit is pulling everything from before the angular stuff together. All right, so the only new stuff here is the angular stuff. Everything else is the same old business. It's just it's inflated because there's more things to track in this system here. So we could going to leave this left initial kinetic energy alone. What is I, the rotational inertia of the skater ring mess? Well, there is that mass of the there's an mr squared associated with the skater, and there's a little mr squared associated with the ring. And instead of omega squared, remember omega is v over r, I could just have v squared over r squared plus this work done by friction. So the thing I want to be clear about here is this rotational inertia is all bottled up here in that. And omega squared is just a v squared over r squared, just like up here. So that's the only thing that changed in this transition. Don't want to do too many things at once. Things get out of hand. So I want you to see that this r squared is common to both of those terms, so it literally drops out. And we have half mv naught squared equals 1/2 m plus m v squared plus the work done by friction. So the nice thing here is that these rotational things frequently translate nicely into linear terms, which is our goal because I need the linear speed of the skater, the initial speed when the skater hits the ring. All right. So what can we do here to simplify things up a little bit? Well, I can multiply everything by 2. And so, of course, these halves drop out, and I would have mv naught squared will equal m plus mv squared plus 2 FL. Now, one of my speed terms is the speed term I need to solve for, initial speed, the v sub 0. One of my speed terms is the speed term I don't need to solve for, the final speed. But lucky us, right up here, I can change v to be something that's a function of v naught. I can insert this m over m plus m times v naught, and now my v squared could become some sort of weird factor of v naught squared. And then I have the one speed term that I need to solve for. I can isolate that algebraically. So mv naught squared would equal m plus little m. And now I'm going to put v in. So this is going to be m over m plus big M times v naught, that whole mess squared, plus 2 FL. Now, we can go through a lot of algebraic maneuvering, but here's what's going to happen. We're going to get I'll skip some math here. V naught squared. Well, one thing you can know here is that m plus m that's in blue is going to kill one of those m plus m that gets squared. You have an m squared over a quantity little m plus big M squared. So one of those gets canceled out and stays, but one stays behind. And you get all these other squared things. And so in the end, I'll skip to, we get, of course I skipped a few steps, so no worries. When I bring that whole term to the other side and do some simplifications, I get that. And this is all going to be equal to 2 times the work done by friction, double the work done by friction. And so now, notice that these m squareds wipe each other out in the top. And I have this right here. Oh, by the way, this is a plus. Be careful with that. Got things wired there. And we will have V naught squared equals double the work done by friction times m plus m over the product of the two, the sum of the masses over their product. Now, they didn't, we could take the square root right now and we would have an equation, but it wouldn't have the radius of the ring attached to it if we just did it right here. So what I need to do now is we need to change this work done by friction term to involve the things that we needed to pay attention to, like the mass of the skater, mass of the ring, and all these other stuff. So right now, big M and little m are accounting for mass of skater and mass of ring. I have my initial speed term in here, but I don't have what has been asked, which is minimum speed that the skater has in terms of the radius of the ring. I don't have that in here. And so let's take our, we need to add a page here because I'm out of space. So I have, whoops, V naught squared equals 2 double the work done by friction, and it was the sum of the masses over the product of the masses. Well, this length, this work done by friction, is on a circular path. So the length associated with the work done by friction is the circumference of 5 circles. It's supposed to go 5 times around the pole, which guarantees a circular path, because there's a constant radius around that motion. So length, okay, L is just going to be 5 times 2 pi, or 10 pi. That's what length's going to be. Friction, this thing right here is just mu mg, or mu times the normal force, and in this case the normal force is the weight of the skater. Okay, so let's, since that's capital M, let's, let me erase that here. So mu n, which will be mu capital M for mass of the skater G. So let's see how this shakes out. It's like a Russian doll with all these equations, all right? So I'm going to have 2 times 10 pi, or 20 pi, times mu m g times m plus m over mm. And what happens here is I get these mass of the skaters drop out. So V naught squared would equal 20 pi mu. Oh, wait a minute. What did I leave out of the length equation? Looking yellow. Two pi what? Circumference of a circle. What's the circumference formula for a circle? Isn't it 2 pi r? Right? So I left an r out. So, which is sad because it was right here on my notes. There's an r in here. So 20 mu pi rg times the sum of the masses over the little mass of the ring. Take the square root of both sides, and V naught of all of that. So, because nothing is squared in there, I could maybe pull a 4 out of the 20, but that really wouldn't do us much good. So what we've obtained here is a speed function. This will tell us the initial speed required for this skater to go around the pole 5 times. It incorporates the work done by friction, except I don't have the frictional force term explicitly in it. Though I could have just left it. I could have left the frictional force in as mu in, but it's been in there. So now I have it just in terms of mass and radius and constants. So the force of friction is being accounted for by mu, the coefficient of friction. The work done by friction is accounted for in the radius there and the 20 pi r business, and then the mass of the things involved in the system. So if we make some assumptions here, so let's say we'll just make it easy. If radius is 1, if mu is really small, like 0.1, let's say that the mass of the ring is 5 and the mass of the skater is 50. And let's keep G as 10. So these are all nice numbers to play with in our function here. What does this turn out to be? If I did everything right here, I should get 8.24 meters per second. Would be the speed of that skater. So that's a lot of work to figure this out. So now, but this formula would apply if somebody said, oh, we need the rings to be bigger. Or when we first tried it, these rings were their mass wasn't sufficient and they broke or they bent or something. All right, so we'd have to change, but all we'd have to do is come back and change a number. And how does this work? So the other thing they could do is, all right, if it needs to obtain that speed, then maybe we'll have them come down on ramps that are high enough. So we could work backwards to how high should they come down from. That way nobody has to do anything but just step over the edge. If they do that at the same time, everything looks perfect. It's all about aesthetics for solving this kind of problem. All right. The next one. Space station. One. So is the energy and center of mass is at the beginning of this one. You're going to design a space station. It has 4 different habitats. And these have different masses. 10 times 10 to the 5th kilograms, or you could say 1,000,000 kilograms, be the same thing. 20 times 10 to the 5th kilograms, that's going to be 2,000,000, etc. So we have these masses, and they're large. And the entire space station has to spin so that there's an experience of artificial gravity. And the space station is going to have 1 kilometer side. So it's a square with an edge of 1 kilometer. Okay? And I think you can already tell the center of mass is going to be offset a little bit. All right? But so what? We need to do it this way. And so we're going to work it out this way. Axis of rotation will be perpendicular to the plane. So imagine this thing laying flat, a square with 4 corners where the masses are. And it's going to rotate around its center of mass, which inevitably is not going to be in the very middle. So it's going to be this weird wheel that has legs that are shorter than some of the other legs, but it'll spin around whatever its center is. So we've got to find the center of mass and the radius that each station will have relative to it. So really what we're doing here, picture-wise, is there would be these 4 points, these 4 point masses, and so this the square here that they're on. So they're not this highlighting is just a so this is a 1 kilometer, and this is 1 kilometer, and somewhere in the middle of all of this, but not in the exact middle, will be the center of mass. And so we're going to have some sort of arms going off in this direction, that direction, that direction. That was a pretty bad one. And we're going to get this thing spinning, around the center of mass, wherever the center of mass is. All right? Why they didn't build it so that it was in the exact middle, who knows? We got our reasons for whatever we're doing. So this is the picture of our system, all right? And so we'll have, mass 1 here, mass 2 here, mass 3 here, mass 4 there. And this is going to be some sort of, this center of mass will have there's going to be an x and y coordinate for the center of mass. All right? So that's our goal, is to construct the system and get it spinning and figure out how much energy it takes to get it spinning. It says that we want it to spin at 5 meters or 5 revolutions per minute. All right, so we're going to go 5 revs per minute. 1 rev is 2 pi radians. And a minute has 60 seconds. So we crunch all of those numbers, and we're going to get 0.524 radians per second, half a rad per second. That's pretty slow. Okay? But given how big this thing is, it's going to take a lot of energy to spin something that's 1 kilometer on its square side at any speed. So now we have that angular speed that we're inevitably going to need to finish the deal here. So those are preliminaries out of the way. We need to find the center of mass of the station. We're also told that the connectors, the thing that connects all of the edges to the corners to the middle, has a negligible mass relative to the masses of the stations, so we're going to ignore whatever those arms weigh in this case. In reality, we wouldn't. We would account for every last ounce, so to speak, every gram. So center of mass. So if I put the the 4 megakilogram one here and the 1 megakilogram one here, that gives me 50 megakilograms above. And if I put the 2 megakilogram one here and the 3 megakilogram, that's just the, instead of 10 times 10 to the 5th, I'm just going to write 1 times 10 to the 6th megakilograms. That means I have 50 above and 50 below. That means my Y center of mass is going to be 0. I don't have to do any math in that case. But when I look from left to right, I have 6 megakilograms on the left and 4 megakilograms on the right. So what this means in this arrangement is I'm going to be off center to the left. I'm going to have a negative x coordinate for my center of mass. All right? So center of mass calculation, it's always the sum of the masses in the bottom. So 1 plus 2 plus 3 plus 4 megakilograms. It's the total mass. And then I'm going to have all of these position mass products. So if I arbitrarily, and I'm going to do this, there is technically, if I'm, have an origin of the system, that means that each one of these masses is 500 meters left and right and 500 meters top and bottom of the middle of the square. Okay? So I'm choosing the square to actually have a center that I'll call 0, and that means that every one of the xy coordinates is plus or minus 500 for each coordinate. You're either up 500 or down 500 on y. You're either left 500 or right 500 on x. Okay, so it makes it easy. So the first one, if I do the top right one, since it's positive, so that'll be at 500 meters times 1 megakilogram, and I'm going to subtract from it, or I could just say plus a negative, its left-hand side, 500 meters, and that's a 4 megakilogram. So that's the top part. I have a difference across that, and then the bottom part will be a plus 500 meters, because it's over to the right, as far as its position goes, and a 3 megakilogram minus 500 meters times the 2 megakilograms. So if you do all of that number crunching, I'm going to get an x center of mass that is negative 100 meters. All right? So I now know that the center of mass is minus 100. Now, what am I going to do with that? Good question. Glad you asked. So I'm going to kind of redraw my square. And I know that it's off left like I originally thought. That's a perfectly straight bars. All right. So basically the two arms on the right have the same length, and the two arms on the left have a length that they share. So I only have really 2 radii to compute here. And what this means is on this side here, this one's going to be, since I cut in 100 to the left, That means the width of these two smaller triangles is 400 meters. The height's 500. So guess what, Pythagorean's theorem, if I do 400 meters squared plus 500 meters squared and I take the square root of that, I'm going to have the length of that hypotenuse. And that's going to be what the radius is on the left. And then this one here is the rest of the kilometer width of 600, and this one's still 500. All right, so radius 1 will equal radius 4, using the numbers from above. They'll both have the same structure of 400 squared plus 500 squared, and that's going to give you 640 meters. And radius 2 will equal radius 3 on the right-hand side, and that's going to be 600 squared plus 500 squared, and that's going to be 781 meters. So now I know those radii, which is going to be critical because what always shows up in an angular, a rotational energy problem? I'm going to have that R that's associated with some mass. So rotational kinetic energy, because we want to know how much energy it takes to do this. And it's rotating, so that means I need rotational kinetic energy, which we know to be 1/2 I omega squared. Well, that means I'm going to have 1/2 of basically mr squared. But I have 4 mr squareds. Okay? All the masses are different, but 2 radii to deal with. All right? So in this middle term for I, okay, I'm going to have the m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. And then all of that has the same angular speed. I mean, I could have written out 4 separate terms, but they all have the same angular speed. All right? So now it's literally a plug and chug maneuver. And I am going to spare writing all of that out, okay? Because it's just a computation. And what we're going to get is 6.72 times 10 to the 12th joules. 6.7 trillion joules. Okay, is it feasible to produce 6.7 trillion joules? The answer is yes. Okay, this is less energy than it would take to lift this thing into space. This amount of energy would only get it about 1/3 of the way off the ground. All right, and so if we were to basically let this equal mgh, this would lead to a height of roughly 29 miles. So actually that would be about halfway to space, 60 miles or so, 80 to 100 for good measure. So if I can put it on a Saturn V rocket or whatever we're using these days, if I can get the space station, these pieces into space, then I can get it spinning in space. Just a matter of getting the right rocket up there to do this. If we're lucky, part of the system are thrusters on each pod or somewhere on near the pods. We'd want them out far instead of in the middle. And so that's the thing. If I can get, if the pods include the thrusters, then problem solved. All right. So we don't know what the mass is comprised of. The mass could include fuel and thrusters at each pod. And of course, since they're at different locations relative to the middle, they'd have to fire at different thrust values. But that's just another calculation that the computer controls. All right? And so this works. We could do this. I don't think we've, I don't know how big the current space station is. Never bothered to. I don't think it's a kilometer wide, though. Pretty sure of that. All right. One more problem. This one's pretty easy compared to the other ones. So Star Wars movie. And we're trying to do scientific accuracy. So guess what? Movies that involve all sci-fi movies, in fact, pretty much all movies, one or more physicists, engineers are paid consultants so that as much as possible, this is realistic, okay? But somebody has to compute, like when stunt people jump off of trucks onto another truck or off a bridge onto a truck. Somebody has to know, you know, when do I jump so that I land, okay? Because I'm going to fall 20 meters, you know, da-da-da-da. So somebody does the math on this, all right? And so somebody gets paid. So in reality, somebody's doing this, and of course they make up stuff like hyperspace and wormholes and whatnot. So in this scene, the hero escapes by putting her spaceship through a wormhole. Engines have failed, so the ship is coasting when it pops out at another part of the galaxy, and it goes right in the middle, wouldn't you know, of a binary star system. And so smack dab in the middle, pops right into that spot. Want to know what speed is required so that it doesn't get trapped in this system. All right? So know this. At this point, there is a gravitational potential due to 1 and a gravitational potential due to 2. All right, that's what we're dealing with. And this gravitational potential energy in general is written as, looks a lot like Newton's law of gravity, except it's the work done by this force, which is why one of the r's is missing, because we multiplied that force times the length, separation length, and so you lose that degree in the denominator. And so that means both of these they're identical. According to the problem, the stars are identical mass. The person popped right out in the middle, so really I just have a couple of these terms here. So I'm going to have U1 plus U2. That needs to equal the kinetic energy, or the 1/2 mv squared. So if the speed of the spaceship, if the energy associated with that speed is equal to or greater than the potential energy of the system, then they can escape being trapped by the binary star. If their kinetic energy is less than the potential energy system, then they will not escape the gravity. All right? And everybody dies, and that's terrible. Be like Rogue One, everybody dies. Okay? Finally happened in a movie. So I'm going to have the same two masses because both of these stars have a big M mass that's identical, and the ship has a little m mass. So in both cases, I'm going to have a little m, big M. The distance r is the same in both cases. And that's half mv squared. So really I just have 2g mm per r is half mv squared. And so if I multiply both sides by 2, divide both sides by m, then at the end of this I get a v squared equals 4g m over r, which means v is just going to be 2 times the square root of gm over r. I'm hoping this looks familiar because when we did our moon voyage lab, that Python thing where we made the thing go loop-de-loop around the Earth and the moon, we figured out, so we want to compare this to normal orbital speed. Okay, so if there was just one star to maintain that radius with, we would have the net force equals ma, which means Newton's gravity, g big M little m over r squared, would equal mass times centripetal acceleration. Okay, we did this a little bit ago. And of course, this r is going to wipe out one of those r's. That m is going to wipe out that m. And we'll get v squared equals g m over r, which means v would equal the square root of gm over r. Notice the similarity here. I have double of this. So the orbital speed, remember we did this to figure out what would it be just to get it to go around the Earth at a perfect circle. But just square root of Newton's constant mass of the big body over the radius of separation. And so now if I have two bodies to deal with, it just ends up being double. So this actually makes some sense. It corresponds to our normal sense, which not many people are aware of. Orbital speed is square root of gm over r, unless you take a physics course. All right, so we've done it. All right, and that's a wrap.